and welcome to our channel. In continuation to the last video of the machine learning series about overfitting and underfitting, let us take a step further and learn about bias variance trade-off. Any machine learning algorithm cannot be a 100% accurate one. There exists a slight difference between the actual output value and the predicted output value. This difference is known as error. Error is the difference between the actual output and the predicted output. The goal of any machine learning model is to minimize the error. Models are assessed based on the prediction error on a new test dataset. For example, while predicting the rainfall, we take into consideration factors such as temperature, humidity, atmospheric pressure, and wind. We assume that it will rain if it is a little humid, and it won't rain in case of a windy weather or high temperature. But in reality, our predictions may not be correct each and every time. Note that the factors such as temperature, humidity, pressure, and wind are independent variables, and the prediction of rainfall depends on these factors. Mathematically, let us assume that x is the input variable or feature and y is the output variable or label for a machine learning model. F is a function that maps the input to the output. Then the error can be expressed as the summation of the difference between the actual value and the predicted value. Error can also be written as the sum of reducible error and irreducible error. Irreducible error. It refers to the error that can be caused by some unknown variables having an influence on the output variable. For example, while predicting the demand for a particular product, there could be some unknown factors like natural calamities or new technology which are completely out of our control but affect the model's performance. The error caused by such factors is called as irreducible error. Reducible error. It refers to the error that can be reduced by improving the model. It comprises of two terms, namely bias and variance. Bias. Bias is the difference between the average prediction of our model and the correct value which we are trying to predict. A model with high bias pays very little attention to the training data and oversimplifies the model. This causes errors in our predictions. Variance. Variance is the variability of a model prediction for a given data point or a value which tells us the spread of our data. A model with high variance pays a lot of attention to training data and does not generalize on the data which it hasn't seen before. Hence, the model performs well on training data but has high error rates on test data. The effect of bias and variance on the model can be understood with the help of the Bullseye diagram. Here, the center or the bullseye is the model result which we want to achieve. This point is where the model predicts all the values accurately. As we move away from this point, the accuracy of the model goes on decreasing. A model with high bias and low variance is very far away from the bullseye, but the predicted points are closer to each other as the variance is low. From this, we can say that the algorithm of the model is not complex enough to capture the underlying trend of data, and hence the model is an underfitting model. On the other hand, a model with low bias and high variance will predict the points closer to the center, but it is inconsistent as the points are far away from each other. This means that the model has learned the data too well and thus it is an overfitting model. To avoid both these conditions and to strike a balance between them, the term bias-variance trade-off comes into picture. If our model is too simple and has very few parameters, then it may have high bias and low variance. Similarly, if our model has large number of parameters, then it's going to have high variance and low bias. So we need to find the right or good balance without overfitting and underfitting the data. This trade-off in complexity is where there is a trade-off between bias and variance. Hence, to achieve a bias-variance trade-off, we need to reduce high bias and high variance. To reduce high bias, we need to add more input features, add more complexity by introducing polynomial features to our model, and decrease the regularization term. Similarly, to reduce high variance, we need to add more training data, reduce the input features, and increase the regularization term.
Thus, to build a good model, we need to find the perfect balance between bias and variance such that it minimizes the total error. Total error can be expressed as the sum of bias square, variance, and irreducible error. So this is the graph of model complexity versus the error. We see that the total error is minimum where we have an optimum model complexity and there is a balance between the bias and the variance terms. So that's it about the bias variance trade-off. Thank you for watching this video.